Steady heat transfer from finned surfaces, which includes finned surfaces analysis, and assessing how efficiently and effectively fins could enhance heat transfer. We consider steady operation with no heat generation in the fin, the thermal conductivity K of the material to remain constant, and the convection heat transfer coefficient H to be constant and uniform over the entire surface of the fin for convenience in the analysis. Fin analysis aims to estimate the overall heat transfer rate and temperature variation along the fin. The temperature of the base to which the fins are attached is typically known in advance. The boundary condition prescribed at the fin base is a specified temperature as shown in equation 359. If we recall the previous video, we can remember that the typical boundary conditions at the fin base and fin tip are infinitely long fins, negligible heat loss, specified temperature, and convection. For a sufficiently long fin of uniform cross-section, the temperature of the fin at the fin tip approaches the environment temperature T infinity, and thus theta approaches 0. This condition is satisfied by the function e to the power of negative mx, but not by the other prospective solution function e to the power of mx, since it tends to infinity as x gets more significant. Therefore, in this case, the general solution will consist of a constant multiple of e to the power of negative mx. The value of the constant multiple is determined from the requirement that at the fin base, where x equals 0, the value of theta is theta subscript b. Noting that e to the power of negative mx equals e to the power of 0 equals 1. The proper value of the constant is theta subscript b, and the solution function we are looking for is as shown. This function satisfies the differential equation and the solution's requirement to reduce to theta b at the fin base and approach 0 at the fin tip for large x value. Noting that theta and m are given as shown. The variation of temperature along the fin, in this case, can be expressed as illustrated in equation 36T. The steady rate of heat transfer from the entire fin can be determined by Fourier's law of heat conduction. A very long rectangular fin is attached to a flat surface in this example. The temperature at the end of the fin is essential to the surrounding air at 20 degrees Celsius. Its width is 5 centimeters, thickness is 1 millimeter, thermal conductivity is 200 watt per meter Kelvin, and base temperature is 40 degrees Celsius. The heat transfer coefficient is 20 watt per square meters Kelvin. We will estimate the fin temperature at a distance of 5 centimeters from the base and the rates of heat loss from the entire fin.